The art of algorithm implementation, mastering practical programming through code execution in the world of computer science. An algorithm is often described as a set of instructions designed to perform a specific task. However, translating these abstract ideas into functional code requires careful consideration, precision, and deep understanding of both theoretical foundations and practical applications. Algorithm implementation bridges the gap between mathematical logic and real-world software development. It involves taking conceptual algorithms from research papers, textbooks, or whiteboards and converting them into working programs that solve actual problems efficiently and correctly. Understanding the core principles of effective implementation and effective algorithm implementation begins with a clear comprehension of the problem domain. Developers must fully understand what the algorithm aims to achieve before writing any lines of code. This foundational knowledge ensures that every step taken during implementation aligns with the intended outcome. Misinterpreting requirements can lead to significant errors down the line. For instance, implementing a sorting algorithm without considering edge cases such as duplicate values or empty arrays may result in incorrect outputs or program crashes under certain conditions. To avoid such issues, developers should break down complex algorithms into smaller components. This modular approach allows for easier debugging, testing, and optimization at each stage of the process. Modular design, breaking down algorithms into functions or classes, improves maintainability and reusability across different projects. Test cases, writing unit tests for individual components helps identify bugs early in the development cycle. Error handling, anticipating potential failures through try-catch blocks or validation checks enhances robustness. Additionally, choosing appropriate data structures plays a crucial role in successful implementations. Different algorithms have varying performance characteristics depending on how they interact with underlying data types. Data structure selection influences time complexity, space usage, and overall efficiency. A well-chosen structure can significantly reduce computational overhead while improving memory management capabilities. Choosing appropriate data structures for optimal performance. Selecting the right data structure depends heavily on factors like access patterns, insertion/deletion frequencies, and storage constraints. For example, when dealing with frequent lookups by key value, hash tables offer near constant time complexity O(1), compared to linear search methods which take O(n). Arrays provide fast random access but slow insertions/deletions due to their fixed size nature. In contrast, linked lists allow efficient additions/removals anywhere within the list, although accessing elements sequentially remains slower than array-based approaches. A balanced binary search tree maintains logarithmic time complexity for most operations, making it suitable for dynamic datasets requiring ordered traversal capabilities. Beyond basic structures, advanced options like heaps or graphs also play vital roles based upon application needs. Heaps excel at maintaining priority queues where highest/lowest element retrieval matters most. Graph representations vary between adjacency matrices and lists. Matrix form provides faster neighbor lookup while consuming more memory relative to sparse networks represented via lists. Implementing common algorithms with real-world examples. Sorting algorithms serve as fundamental building blocks in many computing tasks ranging from database indexing systems to machine learning pre-processing steps. Implementing popular techniques like quicksort, merge sort, and bubble sort reveals various trade-offs among speed, stability, and simplicity. Quicksort demonstrates divide-and-conquer strategy by partitioning input around pivot points recursively until sorted subarrays are obtained. Its average case performance of O(n) log n makes it highly efficient, though worst-case scenarios could degrade its effectiveness to O(n) superscript 2. Merge sort guarantees consistent O(n) log n runtime regardless of initial ordering but consumes additional memory proportional to dataset size since it creates new temporary arrays during merging phases. Bubble sort operates by repeatedly swapping adjacent elements if they're out of order until full pass yields no changes, indicating completion. While simple to implement, its quadratic runtime makes it impractical except for small-scale use cases. Searching algorithms similarly exhibit distinct behaviors. Linear search scans sequentially through items checking against target value, whereas binary search leverages pre-sorted inputs, allowing exponential reduction in comparisons needed to locate matches. Binary search's requirement for sorted data introduces limitations unless implemented alongside mechanisms ensuring maintenance of order after updates occur frequently. Debugging techniques specific to algorithmic challenges. Debugging algorithm implementations presents unique challenges because logical errors might manifest only under rare input combinations rather than failing outright. Traditional breakpoints and console logs sometimes fall short when tracing intricate control flows spanning numerous iterations. Visualizing execution paths using tools like debuggers equipped with call stack inspection features becomes invaluable here. These allow developers to monitor variable states at critical junctures, helping pinpoint exact locations causing discrepancies. Logging intermediate results systematically aids identification of unexpected behavior patterns, especially useful when tracking recursive function calls whose depth increases exponentially with larger inputs. Unit testing frameworks support automated verification processes, enabling rapid iteration cycles. By parameterizing test suites covering boundary conditions, corner cases, and typical workloads simultaneously, confidence grows regarding correctness assurance levels achieved. Profiling utilities assist diagnosing performance bottlenecks by highlighting hotspots consuming disproportionate resources. Identifying these areas facilitates targeted optimizations, focusing effort where impact will be greatest. Optimizing efficiency without compromising correctness. Efficiency gains shouldn't come at expense of accuracy. Optimization efforts must preserve original functionality while reducing resource consumption wherever possible. Premature micro-optimizations risk over-engineering solutions, unnecessarily complicating future modifications. Refactoring common code snippets into reusable helper functions promotes cleaner architecture. Eliminating redundancies reduces cyclomatic complexity, improving overall readability and ease of maintenance. Caching intermediate computation results applicable across multiple invocations proves beneficial, particularly when processing identical subsets recurrently throughout long-running workflows. Leveraging built-in library routines instead of rolling custom implementations saves development time and minimizes chances of introducing subtle bugs inherent in hand-coded versions prone to off-by-one mistakes or missing edge case handling. Memory allocation strategies influence cache locality, affecting CPU utilization rates indirectly. Allocating contiguous blocks whenever feasible aligns better with hardware architectures, maximizing throughput capacities available. Evaluating trade-offs between time complexity and space usage. No single metric defines optimal solution quality entirely. Choosing between alternative approaches entails evaluating respective trade-offs involving temporal versus spatial efficiencies according to project priorities established upfront. An O(n) superscript 2 algorithm might prove acceptable given sufficient hardware resources allocated if absolute speed isn't paramount concern, whereas situations demanding real-time responsiveness necessitate stricter adherence towards lower asymptotic bounds. Space-efficient designs become essential when operating within constrained environments lacking expansive RAM availability. Here, prioritizing compact data representation formats takes precedence despite possibly increased instruction counts required for manipulation thereof. Dynamic programming techniques illustrate this balance well by storing partial results temporarily yet strategically discarding obsolete information once it's no longer needed, thereby limiting total memory footprint growth proportionally. Approximate solutions occasionally suffice when precise answers aren't strictly mandatory. Acceptable error margins defined beforehand permit adoption of heuristics yielding quicker approximations at reduced cost without violating service-level agreements governing expected outcomes. Best practices for collaborative development environments. Version control systems facilitate team coordination, managing concurrent edits, preventing conflicts arising from simultaneous modifications occurring independently amongst contributors. Code review practices ensure peer validation, verifying conformance against established coding standards, promoting consistency across entire code bases. This collective scrutiny catches oversight opportunities missed individually, enhancing overall product reliability. Documentation accompanies every public API, exposing rationale behind design decisions, aiding others who'll need extend or modify existing functionalities later without reverse engineering intentions obscured beneath opaque implementations. Automated CI pipelines execute regression tests, continuously monitoring health status, providing immediate feedback upon commits, identifying regressions, promptly minimizing integration headaches downstream. Continuous deployment models enable gradual rollouts, releasing incremental improvements, safely isolating risks associated with wholesale replacements, potentially destabilizing operational continuity unexpectedly. Future trends influencing algorithm implementation strategies. Rapid advancements continue shaping modern landscapes, compelling adaptation toward emerging paradigms, altering traditional methodologies previously considered standard practice. Distributed computing demands reconsideration of sequential assumptions, favoring parallelizable constructs, amenable decomposition across multiple nodes, cooperatively solving aggregated tasks concurrently. Machine learning-infused approaches increasingly replace classical deterministic procedures, offering probabilistic predictions adaptable amidst evolving contexts, resisting static rule sets, becoming obsolete quickly. Quantum computing promises disruptive shifts, redefining feasibility boundaries currently deemed computationally prohibitive, now achievable, leveraging qubit superposition properties unattainable classically. Sustainable computing initiatives emphasize energy-aware implementations, seeking reductions power consumption, aligning environmental stewardship goals without sacrificing functional adequacy, delivering desired outputs reliably, sustainably. Conclusion: mastering algorithm implementation requires balancing theoretical rigor with pragmatic considerations, adapting flexibly amid changing technological landscapes, embracing innovation, responsibly advancing field collectively, benefiting broader communities engaged therein. By adhering principles outlined herein, practitioners cultivate expertise capable tackling diverse challenges, confidently producing high-quality software, consistently meeting expectations set forth initially, guiding undertakings forward successfully, achieving objectives pursued diligently throughout endeavors embarked upon.